Right. Welcome back to the deep dive. Today we're going to be taking a deep dive into this topic of confirmation. You know, how do we know, like, when we've got evidence for something? Like, how does evidence actually work?
Well, yeah, that's right. It really is about, for a philosopher at least, it's sort of the fundamental question of how do we actually reason, I mean, in a way, we're bombarded with evidence all the time, right? But how do we use it to support our beliefs or to change our beliefs or whatever?
Yeah, think about, like, simple stuff. You hear a rumble of thunder.
Right.
Does that mean a storm's coming?
Yeah.
Or, I don't know, like,
Yeah.
I'm trying to think of some other example.
Yeah, sure.
Or, like, the scientists, right? They're looking at, like, a universe-altering theory. They've got all this, complex data. How do they actually use that data to say, yeah, this is good. This is, like, on the right track?
Yeah, absolutely. If you think about it, a lot of the things we believe on the basis of evidence, right? We don't just pluck it out of thin air. So really getting a grip on how evidence works is kind of fundamental to figuring out, well, what can we know? What are our justified beliefs?
And to make it even trickier, right? It's like Hume pointed out, right? This whole problem of induction. It's like for any given piece of evidence, there might be like a million different explanations that fit it, right? So, how do we sift through all of those and say, this one is the one that's actually confirmed. This is the one that has evidential support.
Right. So, for any given set of observations, there's always going to be a whole bunch of hypotheses that are compatible with it.
Yeah.
So, how do we decide which one of those hypotheses is the one that's most strongly supported?
Right.
That's the whole game of confirmation theory, really.
So, yeah, this whole idea of confirmation theory, I know we've talked about it before, but like, it really is about trying to formalize, right? This idea of, okay, what does it actually mean for something to be supported by the evidence? Right?
Yeah, that's right. So, when we say something like evidence confirms a hypothesis or the evidence supports this belief, we're trying to give, a rigorous account of, well, what does that mean exactly? And so confirmation theory uses, a whole range of tools from, logic and probability theory and so on to try and get a really precise grip on that question.
Yeah, and it's tough.
Yeah, it's really hard. And even, what seem like pretty simple cases, when you start digging into them, you realize that there's all this, hidden complexity there.
It's deceptive.
Yeah.
It seems simple on the surface.
Yeah.
But it's very, very deceptive. And for us philosophers, it's really important, right? Because we're trying to figure out, okay, how is knowledge even possible?
Yeah, that's right. If we want to understand, what it means to have justified beliefs, then we need to understand, how evidence actually works.
Right? How it all fits together. And especially for, like, science.
Right.
Because we think of science as this kind of paradigm of, rational inquiry and, getting at the truth about the world.
Right.
So we've really got to understand, okay, how is it that scientific theories, which are often like these grand sweeping, explanations for the world, how are they actually supported by the, often very specific and very particular evidence that we have?
Right. And we've got a whole tradition in philosophy going all the way back to, Hume, of looking at science and thinking, well, look, it does incredibly well, but how can it possibly work? I mean, it's clearly, not straightforwardly deductive. You're not just reading the laws of nature straight off the data, right? You've got to be doing something else.
Right.
And confirmation theory is an attempt to, really systematically explore, well, what is that something else?
Okay, so for our deep dive today, we're actually pulling from a really fantastic resource, right? The Stanford Encyclopedia Philosophy article on confirmation theory. We'll put a link to that in the show notes. But, it really nicely lays out kind of the three main approaches to confirmation theory. We've got confirmation by instances. We've got hypothetico-deductivism, the HD, fans out there.
The Kiki crew.
And then we've got the probabilistic approaches, which, of course, Bayes is going to be in there somewhere.
Right, exactly.
So let's start, I guess, with the, maybe the simplest one to grasp first, confirmation by instances. And this really goes back to, this idea that, okay, if we have a hypothesis, like, all F's are G's, like all ravens are black.
Right.
Every time we see an F that's also a G, that should lend some support.
Yeah, that's right. So the more instances we find, the more F's that are also G's, the more confident we can be.
Right, right.
It's like, well, okay, we've seen a bunch of ravens and they've all been black. So maybe there's something to this idea that, all ravens are black.
Right, right. And that's kind of like the, NICOD, right?
Yeah.
He's one of the philosophers.
Yeah, that's right. So Jean Nicard, back in, I think it's the 1920s or so, came up with this really simple but powerful idea, which is that, well, if you find a case where, you've got F and G together, that supports the claim that all Fs are Gs.
Okay.
And then if you find a case where you've got F and you don't have G, that goes against it.
Okay, so that seems pretty straightforward. But then Hempel came along and kind of, Hempel loved to formalize.
Yeah.
Like take these vague notions and make them very precise.
That was his thing.
Yeah.
It was all about rigor.
Super rigorous.
Yeah, absolutely.
So he kind of came up with like a whole system around this.
Yeah, so he introduced, some terminology that's, a little bit technical.
Okay.
But I think it's really useful for kind of teasing apart the different aspects of, this idea of confirmation by instances.
Yeah.
So he talks about, having an evidence statement, which is basically, a statement describing what we've observed. And then we have a hypothesis, which is the general claim that we're interested in.
Okay.
And then he defines this thing called the E-development of H, which is basically taking your hypothesis and restricting it to just the individuals that are mentioned in the evidence statement.
Okay, so can you give like a concrete example of how that would actually work?
Yeah, sure. So, let's stick with the ravens example.
Sure.
So the hypothesis is all ravens are black.
Okay.
And the evidence statement is raven is black. So A is some particular raven that we've observed. The E-development of the hypothesis in this case would just be raven is black.
Okay.
Right, because we're just taking the general claim all ravens are black and we're applying it to the specific raven A that's mentioned in the evidence.
Okay, I see. Okay, so that's the E-development. So then how does Hempel use that to define confirmation?
Right, so he says that you have direct Hempel confirmation if the evidence statement logically entails the E-development of the hypothesis. So in our ravens example, raven is black, directly Hempel confirms all ravens are black. Because if raven A is black, then it follows logically that raven A is black, right? That's just like a trivial entailment.
Okay.
So the evidence statement guarantees the truth of the E-development, and that's what direct Hempel confirmation amounts to. But he also has this broader notion of Hempel confirmation, which is where the evidence statement entails the E-development of some other statement, and that other statement entails the hypothesis.
Okay, so it's like a chain.
Yeah, like a chain of entailments.
Okay.
So, maybe the evidence doesn't directly tell you anything about ravens being black, but it tells you something about, some other property that ravens have.
Okay.
And that property, in turn implies that ravens are black. So you get this sort of indirect support for the hypothesis.
Okay, so we've got the direct version, the kind of chained indirect version.
Right.
And then, of course, Hempel being Hempel, he's got to have the opposite.
No, opposite, yeah.
Like, okay, so how do we define disconfirmation then in this framework?
Right. So he defines, direct Hempel disconfirmation in pretty much the analogous way. So instead of the evidence entailing the E-development of the hypothesis, it entails the E-development of the negation of the hypothesis.
Okay.
Right. So if the evidence tells you that, the hypothesis can't be true, then that directly Hempel disconfirms it.
Right. So like a white raven would directly disconfirm all ravens are black.
Exactly, yeah. A non-black raven.
A non-black raven, right?
Yeah. And then, of course, you have the more general notion of Hempel disconfirmation, where, the evidence entails the E-development of some other statement, and that other statement entails the negation of the hypothesis.
Okay, so again, we've got this kind of indirect way of undermining it.
Exactly.
Okay, so that seems pretty, so far it seems pretty intuitive.
Yeah.
Like, okay, white ravens, bad for the all ravens are black hypothesis. Black ravens, good for it. But then, of course, with confirmation theory, there's always a but.
Yeah.
And that but in this case is the Raven's paradox.
Yeah.
Which is so famous and so, mind-bending in a way.
Yeah.
So could you maybe walk us through, like, how does that paradox arise in this very simple system?
Yeah, sure. So, as we said, the all ravens are black hypothesis seems pretty simple, right?
Yeah.
But it turns out that, even this seemingly simple hypothesis leads to some really weird consequences when we start thinking about it in terms of Hempel's theory. So, as we said, if we see a black raven, that Hempel confirms the hypothesis.
Right.
But now let's think about what happens if we see, a white shoe, let's say.
Okay, a white shoe.
So now the white shoe is not a raven and it's not black.
Right.
So you might think, well, that's totally irrelevant to the hypothesis about race.
Totally irrelevant. Right?
Yeah, absolutely. But it turns out that according to Hempel's theory, seeing a white shoe also confirms the hypothesis that all ravens are black.
Wait, what?
Yeah, it sounds crazy.
That's so strange.
But here's how it works. So the statement, all ravens are black, is logically equivalent to the statement, all non-black things are non-ravens.
Okay.
Right. Those two statements mean the same thing.
Okay, yeah. I can see that.
So now, if we see a white shoe, that's a non-black thing that's also a non-raven.
Right.
So that Hempel confirms the statement, all non-black things are non-ravens.
Okay.
And since that statement is logically equivalent to the statement, all ravens are black, it follows that seeing a white shoe also, Hempel confirms the hypothesis that all ravens are black.
So it's like this roundabout way.
Yeah, it's like this indirect confirmation.
Yeah.
And you might think, well, that's just a kind of technicality, right?
Right.
But it really points to this deeper philosophical problem.
Right.
Which is, well, what does it mean for evidence to be relevant to a hypothesis?
Yeah. It feels like relevance is just completely out the window here.
Yeah, exactly.
Yeah.
It seems like anything can confirm anything if you just do enough logical gymnastics.
Right. Right.
And, philosophers have come up with this kind of colorful name for this problem. They call it the problem of indoor ornithology. Indoor ornithology.
Yeah.
Catchy.
Yeah. So the idea is that if, seeing a white shoe confirms all ravens are black,
Mm-hmm.
then, you can just stay inside your house all day.
Right.
And just look around at all the non-black, non-raven things, and you'll be confirming the hypothesis about ravens.
Which just feels wrong.
Yeah, it just feels deeply wrong.
That shouldn't count.
Right. It seems like there's got to be more to confirmation than just, these logical relations.
Okay, so that's the Ravens paradox. And then we've got, of course, Goodman had to come along and, win up everybody.
Yeah.
And come up with an even trickier version of this, right?
Yeah, so Goodman came up with this paradox that involves this really strange predicate blight, which he just invented.
It's like a made-up word.
Yeah, it's totally made up.
Yeah.
So an object is blight if and only if it's black and it's observed before some specific time, t.
And it's white if it's observed after time t.
Okay, so it's like this weird time-dependent color.
Yeah, exactly.
Well,
So now let's go back to our ravens hypothesis. All ravens are black.
okay.
But now let's introduce a new hypothesis. All ravens are blight.
All ravens are blight. Okay.
And let's say we observe a raven before time t,
Right.
and it's black.
Okay.
So it seems like pretty normal evidence, right?
Yeah, a black raven.
Yeah.
Before this weird time.
Yeah. But now the problem is that according to Hempel's theory, this observation confirms both hypotheses equally well.
Wait, both?
Yeah, both.
Like all ravens are black and all ravens are blight?
Exactly.
Okay.
Well, the reason is that, if you think about the E development of all ravens are black for this observation,
Okay.
it's just this raven observed before time t is black.
Okay.
Right. And that's entailed by our evidence because we did observe a black raven before time t. But now, if you think about the E development of all ravens are blight, it's also this raven observed before time t is black.
Right. Because before time t, blight just means black.
Exactly. So the same observation confirms both hypotheses.
Okay, but how can that be? Because all ravens are black and all ravens are blight lead to completely different predictions about the future.
Exactly. Yeah. So all ravens are black says that ravens are always going to be black.
Right.
Whereas all ravens are blight says that, well, they're black before time t.
Right.
But then after time t, they're going to be white.
So it's like this weird time-traveling raven
Yeah.
that changes color.
Right. And so the same evidence seems to be confirming these two contradictory hypotheses.
Okay, that just seems like a mess.
Yeah, it's a mess.
Like Hempel's system seems totally broken at this point.
It really puts a lot of pressure on Hempel's theory, right?
Right.
Because it seems like, well, something's got to give.
Right, right.
Either, we have to give up this idea that confirmation by instances can actually work, or we have to say that, there's something wrong with these predicates like blight and grew and so on.
Right. And Goodman's point is that, well, how do we distinguish,
Right.
what's a good predicate and what's a bad predicate?
Exactly.
Like, where do we draw that line?
Yeah, it's really hard to see how to draw that line in a non-arbitrary way.
Right, right.
Goodman's point is that blight is just as good a predicate as black in a way.
Okay, so that's a big problem for confirmation by instances.
Yeah, it's a huge problem.
And, there are other problems as well, right? It seems like this kind of confirmation by instances only really works if, the evidence statement and the hypothesis are talking about the same kind of things.
Yeah, that's right. So if your hypothesis is about ravens being black, but your evidence statement is about, the phases of Venus or something.
Totally different.
Yeah, then it's not really clear how you can apply Hempel's theory.
Right. Because there's no overlap.
Yeah, there's no overlap.
Okay, so this is like a serious limitation then.
Yeah, it's a big limitation.
But didn't Glymer, right, try to like extend Hempel's system to deal with some of these problems?
Yeah, that's right. So Clark Glymer came up with this idea of, bringing in these auxiliary hypotheses.
Auxiliary hypotheses.
Yeah.
Okay.
So his idea is that, a hypothesis is never really tested in isolation, right?
Right.
There's always this whole background of other assumptions that are being made.
Okay.
And those assumptions can be really important for connecting the hypothesis to the evidence.
Okay.
So, for example, if we're testing the hypothesis that, smoking causes cancer.
Right.
Well, we're also assuming, that our methods for measuring smoking are accurate.
Right.
We're assuming that our methods for diagnosing cancer are accurate. We're assuming, all sorts of things about, the biology of the human body and so on.
Right. So there's all these hidden assumptions that are kind of lurking in the background.
Yeah, exactly. And so Glymer's idea is that, we need to bring those assumptions out into the open.
Okay.
And we need to treat them as part of what's being tested.
Good.
So he says that, evidence confirms a hypothesis relative to some set of auxiliary hypotheses.
Okay.
Right? So it's not just a two-place relation between the evidence and the hypothesis.
Okay.
It's a three-place relation.
Okay.
So you have the evidence, you have the hypothesis, and you have the auxiliary hypotheses.
I see. Okay, so that's how he tries to make it more applicable to like real world science,
Oh,
right?
exactly.
Where it's not just these simple little, all F's or G's kind of things. It's much more complicated.
Yeah, it's messy.
Okay, well, I think that's a good segue into our next big topic, which is hypothetico-deductivism.
Yeah.
The HD approach.
Yeah.
So what's the basic idea there?
So the basic idea behind HD is that, evidence confirms a hypothesis if the hypothesis, together with some auxiliary hypotheses, logically entails the evidence.
Okay, so it's kind of like deduction in reverse.
Yeah, that's right. So instead of starting with the evidence and trying to figure out, what hypotheses does this support, we start with the hypothesis.
Right.
And we say, what would we expect to observe if this hypothesis were true?
Right.
And if our observations match those expectations, then that's evidence for the hypothesis.
Okay, so like classic example, right?
Mm-hmm.
Einstein predicting the bending of light.
Yeah, exactly. So Einstein's theory of general relativity predicted that, light from distant stars would be bent by the gravity of the sun.
Right.
And then, during a solar eclipse, astronomers were actually able to observe this bending of light.
Right.
And so that was taken as evidence for general relativity.
Okay, so that's the basic idea. But then, of course, there's got to be some twists and turns here.
There's always twists and turns.
Yeah, because I'm guessing, like Hempel's system, there are some paradoxes or some problems that arise.
Yeah, absolutely. So one problem with the, sort of simplest version of HD is that it leads to this thing called the irrelevant conjunction paradox.
Irrelevant conjunction paradox. Okay, another catchy name.
Yeah, they love their catchy names.
Philosophers do, yeah. Okay, so what is that?
So the basic idea is that if some evidence E confirms a hypothesis H, then it should also confirm the conjunction of H with any other statement Q.
Even if Q is totally irrelevant.
Exactly. So, for example, if observing that, this raven is black confirms the hypothesis that all ravens are black,
right,
then it should also confirm the hypothesis that all ravens are black and the moon is made of cheese.
Okay, that just seems crazy.
Yeah, it seems totally crazy.
Why would that be the case?
Right. And the reason is that, if H entails E, then H and Q also entails E.
Right, because if the flow part isn't true, then adding anything else to it.
Yeah, exactly.
It doesn't change the fact that it entails E.
Right. So if confirmation just amounts to entailment, then this paradox follows.
Okay, so that's a problem.
Yeah, that's a big problem.
And then there's this whole other issue with HD, right? About underdetermination.
Yeah, that's right. So the idea of underdetermination is that, for any given set of observations, there are always going to be multiple hypotheses that are compatible with it.
Right. We kind of talked about that at the beginning with Hume.
Right, yeah. And so the problem for HD is that, if we're just looking for hypotheses that entail the evidence,
right,
then we're going to be stuck with this problem of, how do we choose between all these different hypotheses?
Right, because they all fit the data.
Yeah, they all fit the data.
So how do we decide which one is the best one or the most confirmed one?
Right, and this is where, the auxiliary hypotheses can come back into play.
Okay.
because, often it's the auxiliary hypotheses that are going to make the difference between, one hypothesis being confirmed and another hypothesis being disconfirmed.
Okay, I see.
So, for example, let's say we're trying to explain the motion of the planets. And we have two hypotheses. We have the Ptolemaic hypothesis,
Okay.
which says that the Earth is at the center of the universe and the sun goes around the Earth.
Right, right.
And then we have the Copernican hypothesis, which says that the sun is at the center and the Earth goes around the sun.
Okay.
Now, both of these hypotheses can actually account for the observed motions of the planets.
Right. If you add enough epicycles and things like that.
Yeah, you add enough epicycles and so on.
Right.
So if we're just looking at, whether the hypothesis entails the evidence,
Right.
then it seems like both hypotheses are equally well confirmed.
Right. Right.
But, the Copernican hypothesis is, in a way, a lot simpler.
Yeah, it's more elegant.
Yeah, it's more elegant, it's more parsimonious, it doesn't require all these extra bells and whistles.
Right, right.
And so you might think that, well, that's a reason to prefer the Copernican hypothesis.
Okay.
Even though it doesn't, strictly speaking, entail the evidence any better than the Ptolemaic hypothesis.
Okay, so that's where this idea of simplicity comes in.
Right.
As like an extra criterion.
Yeah, as a tiebreaker.
Right.
So, a lot of philosophers have argued that, simplicity is an important virtue of scientific theories.
Okay.
And that, when we're faced with two hypotheses that are equally good at explaining the evidence, we should prefer the simpler one.
Okay, so simplicity can help to, resolve some of these underdetermination problems.
Yeah, to a certain extent. But, it's also a really tricky notion, right?
Right.
I mean, what does it mean for a theory to be simple?
Yeah, like how do you measure that?
Yeah, exactly. There's no, sort of objective measure of simplicity.
Right, right.
And so it can be really hard to say, in a given case, what hypothesis is really the
Right.
simpler one.
Okay, so simplicity is kind of like a slippery concept,
Yeah.
but it does seem to play some role.
Yeah, it seems to matter.
Yeah. Okay, so those are some of the challenges for HD. But I guess the other big one, right, is this whole problem of old evidence,
Yeah, that's right.
which we've alluded to a little bit already, right?
Yeah.
So how does that problem arise within HD?
Right. So the problem of old evidence is that, if we're just looking at whether a hypothesis entails the evidence, then any evidence that was already known before the hypothesis was proposed can't confirm the hypothesis.
Right, because it's like the hypothesis was designed to fit that data.
Exactly. It's like, you're cheating.
Right, right.
You're just, coming up with a hypothesis that's specifically tailored to fit the evidence that you already have.
Right, right.
And so, a lot of philosophers have argued that, well, that's not real confirmation.
Okay, so can you give like a historical example of how this problem arises?
Yeah, so, one classic example is the case of the perihelion of Mercury. So, back in the 19th century, astronomers had noticed that the orbit of Mercury was precessing in a way that couldn't be explained by Newtonian physics. And this was a big puzzle. It was one of the, sort of outstanding problems in astronomy.
Right, right.
And then, along came Einstein with his theory of general relativity.
Right.
And he was able to show that general relativity did predict the precession of Mercury's perihelion.
Okay.
So you might think, well, that's great. That's evidence for general relativity.
Yeah.
But the problem is that the data about Mercury's perihelion was already known before Einstein proposed his theory.
Okay, right.
So according to HD, it shouldn't confirm the theory.
Right. So this is a serious problem then for like how do we deal with this?
Yeah, it's a big problem. And philosophers have come up with a bunch of different solutions.
Okay.
Some people have said, well, look, maybe HD is just wrong.
Right, maybe we need a different system altogether.
Yeah, maybe we need something else.
Okay.
Other people have said, well, maybe we can tweak HD a little bit.
Okay.
Maybe we can add some extra criteria to deal with this problem of old evidence. So, for example, some people have said that, well, maybe old evidence can confirm a hypothesis if the hypothesis was able to explain the evidence in a way that no previous theory could.
Okay, so it's like a novelty requirement?
Yeah, kind of like a novelty requirement.
Okay.
But, there are all sorts of problems with trying to make that precise.
Right.